All right, so this week we'll finish up. In fact, we'll finish up today with arrays, and then we'll get into some tooling and some debugging. Introduce you to GDB and Valgrind, which you'll be using tomorrow in your lab. But to finish up, that's all in anticipation of next week. So next week is your fall break. There's no class on Monday, and there's no lab on Tuesday, so no lab due that week at all. Your usual due dates of reading and hack will be pushed back to Wednesday, of course, because of that holiday. And then on Wednesday, when we get back, we will have, of course, lecture. That will take the form of a review, just like we did for the first exam. I'll bring last year's, maybe 2 years ago exam. We'll do as much as we want or as much as we can in that review. Because on Friday of next week, which is the 25th, is your second exam. It'll cover everything up to and including arrays, so keep that in mind. Otherwise, there is a hack next week on debugging, which I'll be demonstrating GDB here this week. Last time we left off with multi-dimensional arrays. Regular old arrays that we've been looking at so far, those are one-dimensional arrays. You can look at it like a number line, right? That we've got it only works one way. Well, 2D arrays are tables or matrices, or you can kind of think of them as spreadsheets. In any case, they've got rows and columns. In fact, when you work with your hack this week, you'll be working with 2D arrays in addition to 1D arrays representing images. And images are tables of pixels. So you've got rows of pixels, and then you've got columns of pixels, so that you can manipulate these images and turn them, rotate them or flip them or whatever, right? The way that we're using multi-dimensional arrays is by using two pointers, a pointer to a pointer. And here's the code that we went over last time. In fact, let's open this up again in that visualizer tool. Let's see, there we go. Right. And let's visualize this. Let's edit this and copy and paste what we have there. Right. This is just the default. Ignore that. Right. And it's not well formatted, but who cares? Let me give myself some more room over here. All right, so let's go ahead and start walking through this code. We've got N and M, so we're going to make a 3x5 matrix, or a 3x5 table. 3 rows, 5 columns. Right? The way that we do that is we set up the first row of pointers. We need 3 rows, and so we need 3 pointers to those rows. And that's what happens right here. This table is now pointing to these 3 uninitialized pointers. There's just question marks. Right? This is a pointer to an int star, which is a pointer. So in other words, it's a pointer to another pointer. Right? That's why it's 2-dimensional. On each iteration of this loop, we will set up each row. So that on the first iteration, we set up that first row, which is of 5 elements, M right here, which is just a regular old malloc call like we've been using up to this point. The second iteration will set up the second row. The third iteration will set up the third row. Right? And then you can use it like a regular 2-dimensional array where you've got I and J here, and then we iterate through this and we just set up the values all over the place here. Right? There we go. And then we're done with it, so we now need to clean up. And that's where we left off on Friday. Let's go ahead and edit this code and think about this for a second. What if I were to just free the table? Right? There we go. And what I'll do, instead of going through all that again, I will fast forward to the last frame here and then back it up a little bit. All right. So we've got our array of pointers, but we also have 3 rows of integers. And so when I'm done with it, I need to clean that up. Now, table, what is table? Table is a pointer to this thing right here. Right? What about these 3 things right here? Are they going to get cleaned up? Careful. I mean, it looks like they got cleaned up, but did they really? Right? What ends up happening is this part right here. That gets cleaned up. So what happens to all these pointers? Right? They get cleaned up, cleaned up, cleaned up. But what about these 3 guys right here? Did we ever clean those up? No. Are we able to clean those up? Well, we just lost the pointers to them, so there's no way that we have the memory addresses that we can say, free the first row, free the second row, free the third row. Now, to understand this a little bit more, I want to take this code, and as we have it right now, and let's put it into our demo code over here. Right? This is what you're going to do tomorrow. We can clean that up a bit. What's that thing that if we cut and paste something and it's not well indented, so we need to clean it up? What's that thing called? A style demo.c. Close that, bring it back up, and you see, okay, well, most everything is indented correctly. I'll go ahead and indent that over and indent that over. I don't know why it doesn't do comments, but whatever. But now everything is nicely indented and well formatted. Mostly everything is well formatted. I'm going to go ahead, let's see, I'll increase the size here because we're going to demonstrate something. How do I know if there is a memory leak here? There is a tool that I can use called Valgrind, right? VALGRIND. And what I can do is I can run my program through this other program, and what it'll do is it'll monitor the memory usage, right? And it'll give me back a report of what happens here. Now to do this, what I need to do is I need to compile with first of all, I should always compile with a wall flag, but I'm also going to compile it with a new flag called G. Now G is short for GNU's debugger. It's basically going to preserve function names and variable names and stuff like that. Because, for example, when I actually compile this to a bunch of machine code, it doesn't care that I name my variable table or matrix or my table, right? That variable name goes away. What I want to do is I want to preserve it because I want this program to report back to me that something happened on line 18 or that something happened with this variable called table. If that variable is gone, then there's no way that I can track that back to a variable in my program. So I'm going to use the G flag here to preserve all those symbols. Demo. There we go. All right. Fine. It runs with no problems here, right? Because memory leaks they're not going to cause a crash or anything. It's just a bad practice to get into. So what I need to do is I need to run Valgrind on this now. Right? Valgrind is going to run my program and monitor all of its everything that's going on with it. So let's run this and let's get a report back here. Right? So very at the top, of course, as a copyright notice, whatever, right? There's a heap summary here. When this program exited, 60 bytes in 3 different blocks were used. 60 bytes, 3 blocks. What does that correspond to over here? Yeah, in the for loop we created, how many rows was it? Let me jump to the end here. Back a little bit. There we go. There. So how many rows did I have? 3. Those are my 3 blocks. How many bytes did each row take? There are 5 integers. How many integers does each one take? How many bytes does each integer take? 4. So each row was 5 times 4, 20 bytes. 3 rows, how many bytes is that total? 60 bytes. So is it any wonder that it's reporting that 60 bytes were actually lost there? Right? There are 60 bytes on the heap when I exited this program. Right? 60 bytes and 3 blocks are definitely lost. In other words, there's a memory leak here. Right? It tells you that it was allocated in your demo program on line 20. Right there. That's where we allocated the rows. 3 bytes in 3 blocks were definitely lost. Okay? So let's come back over here to the visualizer and fix this now. Fix this memory leak. I can't just free the table. Right? I have to free each one of those rows. So let's go into another for loop here and free up each row. Free table sub I. On the first iteration, it'll free up the first row. Second iteration, it'll delete the second row, etc., etc. So let's visualize this execution, and I'm going to jump immediately to the end here and then back it up. All right, so there we go. There. All right, so we're about to free everything up here. First iteration, it's going to free the first row. The first row is gone. What happened to my pointer to it, by the way? It's a little skull and no crossbones, but it's a little skull. That has nothing to do with Halloween. That means that it is freed up memory. Death, do not touch this memory. You cannot touch this memory because it's been freed. Right? What about next? We will clean up the second row, and now it's dead. Third row gets cleaned up, and now they're all gone. Now I can free up this array of pointers here. And when I free up the table on line 23, it gets cleaned up. Let's see if that improves. Let's edit that. I don't want to get the line numbers. Let's see if that improves our program over here as far as Valgrind is concerned. Right? So I will come down here, and before I free up the table, cut and paste. There you go. Tab it over so it looks nice. Right? Tab it over so it looks nice. There we go. All right, let's go ahead and recompile. Now remember, you need to leave in the G flag, otherwise it wouldn't tell you. It wouldn't be able to tell you, oh, it happened on line 20. Those lines would be gone. I'll show that to you here in a second. So let's go ahead and run it through Valgrind again. Valgrind, please run my program for me and produce a result here, or produce a report. There we go. So all heat blocks were freed. There's no leaks possible. Clean bill of health here. Right? So Valgrind is an excellent tool to do something like this. Now, again, let's go ahead and get rid of this. In fact, let's get rid of all 4. Let's predict now how much memory am I losing now. So before, no, I'm not going to contribute. All right. There we go. And come on, back up. All right. Before, when I was cleaning up only this thing up here, I was losing 60 bytes right here. Right? How many bytes do you think these takes? That this one takes. Now there are 3 things in there. How many bytes does an integer pointer take? You might think 4, but it's actually 8 because memory is actually big, right? Remember that we've got gigabytes, terabytes, maybe even in some systems, right? So it's 8 bytes for a memory address here, right? And so 8 times 3 is going to be 24. Added to the 60 before, I'm going to expect what? 84 bytes to be lost? Let's try it. GCC. There we go. Valgrind. Right. 24 bytes there. 60 bytes there. I guess it doesn't give me a total. That's unsatisfying. 60 there. There we go. There's my total. 84 bytes in total. Right. Now, what if I had not used that G flag? Right. You could still run Valgrind, but it's not going to give you as much information as it can. For example, it happened in Maine somewhere. I have no idea where it happened. I can't tell you the line number because you erased all the line numbers by not using the G flag. Right? I can't tell you anything about most stuff in there. Right? So a really great tool to use, Valgrind. You'll get some practice using it tomorrow because you're going to fix a memory leak as well. I think that this is already in the notes, but maybe not this. Yeah, here we go. So what I'll do is I will put that last bit in the notes. I guess we don't need 2 frees. That's bad. That's a double free event, and we don't want to do that. I'm also going to show you here how Valgrind can be used to diagnose other issues. Right? So remember that you have a segmentation fault sometime. For example, if we go all the way back to the first week, and you want to read in an integer from the user. Right? So printf, please enter on integer, right? Percent, and then end the line, or no, I'll leave it like that. And then what did I use in the first couple of weeks to read in from the user? Scanf, right? And it was going to be an integer, so %d, and then suppose that we gave it x. At the time, I told you you need to use this magical symbol called an ampersand, and now this week you're getting more practice with that, with your hack that's due today, right? That ampersand gave you the memory address of that thing. Right? If you didn't do that, all you got was GCC. You got a warning, of course. A.out 42. Right? Segmentation fault. Now, you might still be getting segmentation faults, especially if you're doing weird stuff with arrays. Here's how you can use Valgrind to diagnose that a little bit more. So once again, I will compile with the G flag. Just running this as is, does it tell me where I had that segmentation fault? On what line in my program I had that? Nope. I mean, it does on the warning, right? If you read the warning, fine, yes. But here it's not telling you, oh, this program died on line 7 or whatever it is. Line 15 in this case, right? But if I run it through Valgrind, right, having preserved the line numbers and everything like that, 42, there we go. There. It has, up here, no, I don't need that. There we go. Process terminated with a signal 11, that's going to be a segmentation fault. dumping the core. Where did it happen? Well, that's not my code, right? That's scanf. That's standard input-output library code. That's not my code either, right? That's standard input-output library code. There's my code. What line number did it occur on? 15. How do you know that? It occurred in that file, demo.c, on line 15. There's where I go to investigate further. I need an ampersand here. GCC and run it through Valgrind, and you'll get a clean bill of health here. 0 errors, 0 contexts, no leaks are possible, etc., etc. Right? So awesome. Thank you, Valgrind, for telling me that my program is perfect. Right? But you can run it through and use Valgrind for a lot of different things. This is just the tip of the iceberg. You can use Valgrind for a lot of program analysis. It's called a dynamic analysis tool. It analyzes your program as it's running and gives you a report back. Okay? All right. You'll get more practice with that tomorrow. Right? And then we'll use it from now on. Anytime I screw up code, I'm going to immediately fire up Valgrind and find out where it happened. Right? Okay. So with the remainder of our time today, I'm just pulling out our textbook. This is not Zybooks. This is my textbook that does not have auto grading on it. But I've got a bunch of exercises in it, and we'll do as many as we want to remind us how to work with arrays. For example, the first one here is write a function to return the index of the maximum element in an array of numbers. Okay? So let's write that function. I don't need that much real estate anymore. There we go. What should I call this, first of all? Min? Or it was min, right? Or maximum? Oh, it's maximum. So I shouldn't call it min. I should call it what? Max. All right. There we go. Let's document this. This function returns the index of the maximum value in the given array. All right. So if I'm returning an index, what should the value be here? What should the return value be? An integer. Indices are only 0, 1, 2, 3. There's no such thing as the 4.5 element, right? There's only going to be whole numbers there. I'm going to be giving you an array, so const int star array. Why did I put the const in front? So I can't make changes to it. It's not just one integer, it is an array of integers, which is a pointer. What else do I need to give this function? How big it is. Int n. Okay. There we go. All right. Walk me through this. How would we do this? In fact, let's set up some tests right here just to understand how we might implement this. If I had an integer array of values, say 9, 4, negative 9, 3, 0, 5, negative 10, and 5. How many did I put in there? 8. So let's keep track of that in a variable called n, and 8 elements there. Int min index is going to be a call to, or min index, max index is equal to max of array and n. And then I'll say printf max value is at index %d, value is equal to %d, and the line. So that'll be max index, right? And then array sub max index. So for this particular example, what would you expect as an output? What is the maximum value in this array right now? 9? Is that right? Yeah, that's right. I thought I meant to do 10. Okay, that's fine. We'll go with 9 here, right? And what index is it at? 0, right? So it would say the max value is at index 0 and it has a value of 9. Okay. How would you go about how did you do that as a human? You just looked at them all and said, "Oh, that's it, right there." Right? Well, you probably looked at this one and said, "Oh, 9, that's big. That's probably it." But let me go ahead and check the rest of them. Is that bigger? No. Is that bigger? Nope. No. In other words, you went through and you found we're trying to find something that was bigger than what you found so far already. If I had put, say, 10 over here instead, right, then you would have thought, oh, well, 9 is the biggest, 4 is less, negative 9 is less. Oh, I found something bigger. Continue. 5, negative 10, 5. Nothing is bigger than 10. There's my answer right there. How do we codify that? How do we write the code to do that? Max value, okay. What should I initialize it to, right? Because what if that value right there, what value does it have at line 29? Undefined, dead beef, whatever, okay? So what should I initialize it to as best practice? 0? Okay. Careful. That's, what if 0 was not in there? And it's not right now, right? What if everything was 0's not in there and everything is negative? Negative 1, negative 2, negative 3, negative 4, negative 5. But 0's not in there. So, yeah. Let's not do a value. Let's do an index. Right? And we'll start it at the first one. Right? Because certainly the first one, that might be the one that's it. If I change this back to negative 10, then that's certainly the case. Right? All right. I will start by assuming the first one is the max. ... Right? Now, iterate through the remaining elements. If you find one larger, update the max index. Okay? Iterate through the remaining elements. For int I equals something, I is less than something, I plus plus. All right? Where should I start if I'm going to go through the remaining elements? I could start at 0, but on this first iteration, what am I going to be comparing something to? I'm going to be comparing that first one to itself. That seems kind of useless. So where should I start? 1, at the second one. Right? What should I go up to and including? And right, that's the size of the array right there. Right? So if I find something larger, right, if array sub I is larger than what I've found so far, array sub max index, then I will update. Do I return immediately? Nope. I mean, just because you're at the second element doesn't mean that that's the one that's the maximum, right? All right, so what do I do? Update the max index. So max index equals to what? ARR sub max index? Careful, you're getting two things conflated here, a value and an index, and those are two different things. So in this case, it should be the index at which I found that larger element, I. There we go. Do I return here? I would return on the very first iteration, whatever you're going to return. I have no idea what to return there. All right? Do I return here? Yeah, this is where I return. What do I return? Max index. I could have designed this function a different way. I could have designed it the way that you were thinking of, right? I could have designed it so that it's not max index, that it's max, and let's go ahead and take this and say returns the maximum value in the given array. Which way do you want to go, though? Think about, now this is a design decision, right? There's no right answer here, right? There's a slightly righter answer and a slightly less right answer. But you could design both of these functions for different use cases. I want the maximum value. I don't care about the index. I want the index because I'm doing something with it or something. Which one gives more information? Yeah, this one, right? Why does it give more information? If you give me the index, I can always look up the max myself. In fact, that's what I'm doing right here, right? You give me the index, I can always look this guy up right here. So in some sense, this is giving more information implicitly than this one is. So Let's go ahead and keep that. And in fact, let's update the name of this function to be more descriptive. Max index. Right. Max index. There. And then I need to call it max index right here, except that that name change, should I have a variable and a function that has the same name? So let's go ahead and change this to m index. That's good enough. There and there. Go away. GCC this. A dot out. There we go. It looks like it works to me. Okay. The very next exercise is to do the exact opposite. Write a function to return the index of the minimum element in the list or in the collection of, or an array in this case, of numbers. All right. Following the same pattern, what would you do? Copy paste, right? Bad, right? Min index instead. Returns the index of the minimum value in the given array. Once again, let's go ahead and copy paste this. And instead of max index, I'll go min index. I'm going to go ahead and get rid of the cruft. Right? Comments like that should not, we're still seeing that a lot. Comments like I just erased should not be in your final version. Fine, put them in there as a guide for how you want to program it, but go ahead and take them out after you're done. Right? So I took out the cruft there. All right, starting at line 50, what would you change? This should be min index. Right? Change that, change that, change that, change that. Is there anything else that needs to be changed here, though? Okay, you're thinking that you could start at the back and then work forward. You could do that. But what about my criteria here? If you find something that is bigger than the smallest thing that you found so far, update the minimum. Does that sound right? Nope. So what's the only other change here? Yep. Switch that around. Less than. Okay. Let's see if it works. I'm not going to redo this, but I will redo this. Min index and min value is at whatever. Min index, there you go. Right. What's the minimum? What would you expect this to output? I think the minimum is what? -10? And it's at index 7? Or 6? 0, 1, 2, 3, 4, 5, 6. Oh, there's 7 things in there. I've been screwing that up. Or, you know what? Let's retain the 8 and let's add one more. 4. There we go. There. Right. We were getting away with it. Right. In fact, that's a good opportunity to use Valgrind again here. We'll do that in a second here. All right. Works. As a preview towards the end of the semester, we're going to revisit something like this, and we're going to realize, wait a second, I copy-pasted a lot of code here, didn't I? In fact, the only meaningful change here was this one character. Why should I have to write 2 functions that basically do the same thing except for that one character difference? I want to write a generic program that will take care of both of these things, right? And we're going to be able to do that towards the end of the semester. Where we write in a generic way so that you can take this function and it applies to multiple different things so that you don't have to rewrite it over every single time. Right? All right, that's generic programming though. All right, let's go back up here, and I was screwing up the entire time, right? That there were, I said that there were 8 things in there, but there are only 7, right? Oh, there are 8. What was I thinking? Okay, there are 8 things in there. All right, so let's go ahead and add in, or let's take that one away. There are 7 things in there, but I'm trying to access 8 things as if there were 8 things in there. Okay? So GCC. Am I going to get away with it? Yes, I get away with it. Right? It works on my machine, but it doesn't work in CodePost. It doesn't work on every machine. Why? Right? Because there's a hidden bug here. There are only 7 things in my array, but I'm treating it like there are 8 things in it. So this function, when it looks over all these things, and there are 7 things in it, what happens when it gets to the end of this loop? it's going to an eighth thing that doesn't exist. Now, normally I'd like a seg fault out of that, please, because I'd like to know that something is wrong. But the thing here is I'm only screwing up my own memory, right? And C is perfectly fine in letting you do that. But Valgrind, on the other hand, is going to report something like that. GCC. Remember the G flag there. Let's go ahead and run Valgrind on a.out. There we go. There are two errors in two different contexts. What do you think those errors might be? The min and the max. It's accessing memory outside of those arrays. Right, there we go. Conditional jump or move depends on uninitialized values. On line 42, what's going on line 42? We're trying to access something that doesn't exist. Okay. Now, it's not going to give me much information beyond that. On the other one, it's 55 on min index. Right? It's not going to tell me, look, this array only has 7 elements in it, but you're treating it like there are 8 elements in there. So we need another tool for that, and that tool is going to be GDB, which I'll go over on Wednesday. GDB is a debugger. It's GDB. It's a GNU's debugger, right? If I can run this in as a debugger, and I can go ahead and go layout src. Hey, there's my code. Cool. What I can do is set a breakpoint here in main, right? And then I can run my program, right? And I can run it line by line, right? There we go. And I'll step into that function to see what's going on there. Next, 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 next. Where are we now? What iteration are we in this loop here? I don't remember. We can print out a variable. I'm on the 4th iteration because I is now 3. So next, next, next. Oh, we found a new value here, right? What is print array sub I? Oops. Oh, there, it's 10. There's our maximum value, right? What else is in my array? Print ARR at, dereference it ARR at, I think 7 things in there. There we go. There's your array, right? In other words, I can simulate my program through a debugger, and I can stop it and pause it and take a look around, right? I'll just go ahead and continue here. Continue, right there, and it ran through the rest of the program, printed out max value 4 or index 4 value 10, index 6 value negative 10. Right? We're going to look at that in much more detail next time, but otherwise, that's a preview for Wednesday. All right. Let's see, how much time do we have? All right, 20 minutes here. What else do you want to see? Write a function to compute the mean average of an array of integers. Standard deviation. Merging, we won't do that one. We did this one already. Write a function that takes an integer n and produces a new array of size n filled with ones. Find the median of elements. Do a dot product, norm, concatenation. Ooh, that might be good. Here, this one's good. Right. We can do this in the remainder of our time here. Increase the size. It's kind of small. There we go. Write a function that takes 2 arrays and creates and returns a new array that is the concatenation of the 2. That is, the new array will contain all elements of A followed by all elements of B. So, for example, to understand this, suppose that we had an array of, 10, 20, 30, and 40. And then another array, BR, of 50, 60, 70, and 80. And they're both the same size. I want to produce a new array, int cur, that is the concatenation of them. Concatenation, right? Of A, RR, and of size n, and BRR of size n. Right? Basically, I want to take 10, 20, 30, 40, 50. It should be 10, 20, 30, 40, 50, or 10, 20, 30, 40, and then the remainder of this stuff. There we go. That's a good exercise. That's an excellent exercise, in fact. All right. So, concatenation is a good name, good enough name. Right. Good. It's good enough. Right. Maybe there's a better name. I don't know. I don't want to argue about it. In fact, that's a cornerstone of engineering. Engineering, what's better than good? No, nothing's perfect, so that's not attainable. What's better than good? Good enough. It's good enough. Ship it. Go. Done. Right? I don't want to have to worry about that. It meets all the requirements. We're done. Right? So we do need some documentation here, though. This function creates and returns a new array of that is the concatenation of the given arrays ARR and BRR. Right? So I do need to change this. Am I going to be making any changes about ARR? Nope. So const int star, and same thing with BR. N is going to be the size of the first array, and I can't have two n's, so this will be M, the size of the second array. Right? Size M, and ARR is of size N. There. My return value is going to be an int star, or int star. There we go. All right. All right, how am I going to make this new array? First of all, how big is the new array? If the first array is of size n, and the second array is of size m, how big is the new array? N plus m, right? Before, this was of size 4. This is of size 4. I want it to be of size 8. Right? So the new size is going to be int new size is n plus m. Right? Let's go ahead and create it. Int star result. Like we could call it cur. I'll call it result. It's going to be a call to malloc. Right? You want it to be size of integer, however many bytes an integer takes, times the new size. Now I'm wondering whether or not we even need this variable here. We could just put n plus m right here. Right? N plus m. Is that correct, though? Is that correct math? Nope. Parentheses. There, that's correct math. Immediately return that result. There we go. But we need to fill it in now. Right? It's big enough, so what do I need to do now? Copy over the contents of A, RR, ... Then I need to copy over the contents of BRR, ... This one should be pretty straightforward. For int I equals 0, I is less than n, I plus plus. In other words, for each element in ARR, right? Copy it to result. Results of I is equal to ARR sub I. Okay. Again, this is just my basic for loop. For each element in ARR, copy it over to the result. Well, that was easy. Let's go ahead and do the same thing, but for BRR, and there are only M elements in that. Right? Careful. I is starting at 0 here, right? So, I don't know, let's take this over to Python Tutor with a visualization tool and see what we get. Edit this. All right. Yeah. Visualize that. Now this is going to look real ugly. But there we go. All right, so next. There's 10, 20, 30, 40, 50. We'll go ahead and go into this concatenation down here. All right. Those are pointers over to the original ARR and BRR. Right? There's, come on, really? It's way up there. I can give myself some more room here. There we go. There. Next. So that first loop is going to successfully copy over 10, 20, 30, 40, 50. 10, 20, 30, 40. Okay. What's this loop going to end up doing? 50, 60, 70, 80. But where are they going to go? Right there. 60, 40, 70, 80. All right. Why? Because I started out at 1 here. Or it started out at 0, excuse me. All right. So what can I do to this section of code so that I'm copying it in the other part, not the beginning part. Well, let's go back over to the visualization. Where does this first integer start? Or where does this first index start? This 4 here. Where else do you see a 4? N and M, right? The size of the original array, the A array, was 4. So it's going to run from 0, 1, 2, 3. Right? So we need to start copying at n plus 0, then n plus 1, then n plus 2, then n plus 3. Or more generally, n plus I, because I is going to run from 0 up to m. Okay. Let's go ahead and put that into the tutor. Edit this. The only difference that I made was, where is it? There we go. N plus I. Oops. N plus. There we go. Now let's walk through that same process again. Come on. Go down. There we go. Next, 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 next. 10, 20, 30, 40, 50 will be copied. There we go. But now 50, 60, 70, 80 will be copied starting at 4 instead. 50, 60, 70, 80. So this is a great tool if you're trying to conceptualize some of your whiteboard stuff, right? You've written down an idea, you implemented it, it doesn't work. Bring it over to Python, bring it over to pythontutor.com, put it in there and see what's going on, right? It's a visual debugging tool. Over here, Valgrind is it's called TUI, Text User Interface. And GDB that we're going to look at tomorrow is also Text User Interface. This is web-based interface, right? Visual interface, or GUIs, if you've heard of that term before. Graphical user interface. These are text user interface, right? All right, cool. 8 minutes left. Do we have anything else to do? Contains? Okay. That's in your hack. Never mind. I'm not going to do that one. You don't get some free there. All right. Otherwise, these probably get more and more complicated as we go on. Write a function that takes two arrays and determines if they're equal or not. We can't do that in 5 minutes. But there are plenty of other exercises that we could do. Maybe we'll do some on Friday after we've gotten a debugger tool under our belt. But I'll go ahead and leave. Yeah, go ahead.
Do you have the PDF to that on your...
Yeah, this is in the suggested readings. So Canvas. This is your required readings are the Zybooks, but this is just a PDF. So if you go to, come on. So every week we have recommended readings, and then there's the textbook that I'm talking about right there. Right. Like this week, we would recommend chapters 7 and 20 would be on arrays, right? And at the end of chapter 7 are all these exercises. Unfortunately, they're more mathematically oriented than usual. All right. I'll see you on Wednesday.